our eye become larger and larger and we see the things clearly. So here is the eyes. If an object is here, then this is principal axis, okay, and this is the object. If this is object, then this is the angle, yes, this angle 5 degree. If we bring this object here, then this is the angle and this angle is 10 degree. Now this is here, we see the object will appear to be small. Here we see the object will appear to be larger, and with trigonometry, using the tangent, we can find out that this degree, if this degree is doubled, then we will see it double in the size. So this is known as angular magnification. Angular magnification. Okay. When there is an angular magnification, the angle becomes larger and larger. This is here, there is an angle made here. Now I bring it here, there is an angle made here, which is a larger angle. So every part makes the larger angle, and I am able to see all these parts very clearly. So if I want to see anything clearly, the angle made should be large. Okay? So I bring it like this. If I bring the book very close to this, I am not able to read it. That means there is a limit to make the things larger. If I bring it here, it becomes larger. If I bring it here, then this angle becomes 15 degree. It is still larger. Now every time we bring it closer, what we are changing? We are changing u. Now since v is constant, and we are changing u, what we have to change also? The answer is we will have to change f also, and this is how we change the f. The power of turning, we have to increase more and more because the rays are getting now wider. When the things are far away, the rays are coming parallel. They have to be bent a little. If the things are closer, object is closer, the rays are going like this. We have to bend them large to make this sharp image. So they have to come into action, they have to be stressed, and they will press. But what is the limit of that? There is a limit. Here it comes, they press it. Here they come, they press it more. And now we have brought the book very close to our eyes like this. Now they cannot press anymore. If they don't press anymore, then what happens? The image is not formed on the retina. Now the image is formed away beyond it because it cannot bend it further. That means we are not able to see the image clearly. That means we cannot see here. Now we bring it closer, clearer, more clear, more clear, more clear, more clear, and now it has become blurred. I am not able to see. That means this is the best distance from where I see it very clearly, and this distance is very important for us. This is the least distance from the eye, and the thing is clearest. The maximum clarity is there because it is nearest to me. Nearer to me, I will not be able to see it. So this distance, we have given it a particular name. It is the least distance of clear vision. Least distance of distinct vision. Distinct vision. Now this distance we will need a lot. We give it a symbol D, and for a healthy human eye this is nearly 25 centimeters. So when we read newspaper, when we read a book, then we keep the things approximately at 25 centimeters. It may be a centimeter more or less. depending upon eye to eye, person to person. Okay, but approximately 25 centimeter. And we have given it a symbol capital D. What is this? Distance of distinct vision. So remember, this distance is very important. The two things about the eye which are asked in the examination as short questions. What is accommodation? And number two, what is least distance of distinct vision? When it is asked least distance of distinct vision, how will you explain in 2 lines? The thing is, what will you write? When we bring the object closer, it becomes clearer to the eyes. There is a limit where the object is nearest and it is clearest. But if you bring it further, closer to the eyes, it becomes blurred. This least distance where it is most clear is known as least distance of distinct vision, D, and we would like to read, we would like to see things at this distance because there it is most clear. So this is least distance of distinct vision. So these are the 2 features of the eyes. Now how the eyes are working, we have seen accommodation and the properties of eye, what the eyes can do. See what the eyes can do. It is important. Number 1, eyes can roll itself to bring the things in line. Number 2, eyes can control the amount of light entering the eyes. How? With the help of iris. Number 3, eyes are able to make a sharp picture on the retina with the help of what? With the help of lens and ciliary muscles. Ciliary muscle keep on changing and this characteristic is known as accommodation. And the 4th thing is the image is converted into electrical signal or sent to the brain. So these are the 4 work which can be done by the eyes, and all these jobs are related to optics, light. So these are all optical properties of the eyes. Now another small thing we have to learn is are there certain optical defects in the eyes? Why we have to go for glasses and other related things? The answer is yes. So now we will study what are the defects in the eye. Okay, the first defect is myopia, that is short-sightedness. In this what happens? We can see nearby objects clearly. But we cannot see the faraway objects. If a boy is sitting in the last bench and he is not able to see the blackboard, then he has got myopia. He is able to read the book, but he is not able to see the blackboard, that is far away, and this is short-sightedness or myopia. What is the reason for this? What we are going to study is what is the reason for it. First, what is the defect? Second, what is the reason? And third, what is the correction? Okay, what is the reason for myopia? That is shape of the eyeball. A ray coming from distance should meet, after going through the lens, it should meet at retina. Due to some defect, if the eyeball has become like this, short. No, sorry, it's different. If the eyeball has become longer due to some biological defect and it is meeting this way, yes, here, then it is a little short from the retina. It is meeting at a point which is short from the retina, so the name given is short-sightedness. This distance is short. Okay, now we are not able to see the far away object because this. It cannot bend less than this. Due to this shape, the eyeball, which should have been like this, due to some biological defect, it has gone here. Now, the lens, they can increase the power they can decrease the focal length, but they cannot increase the focal length. It is not possible to stretch the lens. It is possible to compress it. So compression is possible, power increasing is possible, but power decreasing is not possible. So the image is formed here. If the object is nearby, then what will happen? The answer is, if the object is here, nearby. Now you see, if this is 10 degree, what we require is more than 10 degree, 15 degree, and that is possible with help of ciliary muscles. So, it is possible. Now what happens? The image is clear. Clear, and here it is not clear. This happens in myopia. So myopia, you just make these two diagrams which shows the far away object not clear, nearby object is clear. Now how do we make the corrections? The answer is, this has to be corrected and this bending has to get little less. So they have to be dispersed. They have to be diverged. If they have to be diverged, we need a diverging lens. So in correction, what do we do? The rays are coming here parallel. This is eye. Normally it will go like this because it is a defective eye. So what do? We put a concave lens here. What is the job of a concave lens? It will diverge like this. If it is diverging in this way, diverging in this way. These are the rays we were not able to see. We have put a lens here, then it is picture for that. Now this lens makes the rays turn this way. If the rays are turned in this way, then again they are bent. And now they are meeting here. Because this angle they can make. This angle it was not able to make. This was a small angle and this is a larger angle. The lens can make larger angle, but it cannot be stretched. It cannot make smaller than this 10 degree, but it can make larger. So we first bend it outside with help of a concave lens and then bend it here, and now it is here. So what is the correction for myopia? Fitting a concave lens. The correction is fitting a concave lens or divergent lens. So once again, what is myopia? We can see nearby objects, we cannot see far away objects. This is the diagram, far away objects we cannot see. Why it is there? Due to defect of the eyeball. The nearby objects we can see it clearly because it cannot bend less than 10 degree, but it can always bend more than that. So this will bend more than that and it is here. So what do we do as a correction? We fit a concave lens which makes it divergent, and now it can bend it sufficiently to make the image on the retina. So this is how we rectify it. Now we have to do the calculation. How do we find that what type of lens or which power of the lens is necessary? So to find out which power is necessary here, we make certain calculations. The calculations are like this. Yes, for this calculation we have to learn about 2 points. I forgot to tell you about those 2 points. So just one line. There is a far point and there is a near point for every eye. Far point, near point. Far point is the point at the largest distance where our eyes can see it clearly. This is farthest point which eyes can see clearly. Okay, for healthy eye, it is infinity. So, for a healthy eye, if the rays are coming from infinity, there is no stress to the ciliary muscles and the lens is able to send them to their focal length, to their focus, which is exactly on the retina. So, this is the for healthy eye, and where is the far point? Far point at the infinity. So, for far point, u is equal to infinity. Okay. Now, what is near point? When we are bringing the object closer, it becomes more and more clear, more and more clear. Now, here it is very clear, but if I bring it here, I am not able to concentrate on it because the image is not being sharp or firm enough. So, here this is the distance where I can see it very clearly. For a human healthy eye, it is 45 centimeter. But if the eye is not healthy, then someone is able to see up to 2 meter. And after that, the things become blurred. So for him, the near point is at 2 meter and not at 25 centimeter. If things are nearer to that, then they will not be able to see it clearly. So that is near point. The least distance where an object can be seen. Object is seen clearly. Of course, it will be very distinct, very clean. But if you bring it closer to that, you will not be able to see it clear. So this is known as near point. Okay, once we know these 2 points, again we come back to the defect. The second defect is hypermetropia, or long-sightedness. In hypermetropia, everything is reverse. Everything is reverse. What does that mean? Can see far off things. Clearly. Cannot see nearby objects. Cannot see nearby objects. Okay. What happens to this with respect to far point or the near point? The near point has moved away. Reason: defect in the shape of eyeball. Okay. This is an eyeball and it has become like this. Now the things, it can see far off objects clearly, far off objects, and they are focused here. If the object is nearby, the rays are coming like this and the ciliary muscles cannot press it beyond a certain limit. They press it as much as possible. Even after that, these are bent only in this direction. In this direction. The image has to be formed here. Then on the retina, how is the image? At the retina, image is not there. So here the image is blurred. Now he cannot see it here. But if we take it here, then this ray go like this, and it has to be bent less. It is able to bend it like this, and able to see if the object is here. So this is known as near point. So this person's near point, what should have been at 25 centimeter, has gone away. Maybe 200 centimeter, 600 centimeter, like that. So this is the defect which is known as hypermetropia, long-sightedness. Again, remember this, cannot see nearby objects. That means cannot read. Very simply you can remember, cannot read. And what was myopia? Cannot see the blackboard, cannot see the faraway objects, cannot see the movies, cannot see the TV clearly. That is myopia. But he can read book clearly. This is hypermetropia. Now how to make a correction in this? Here is the problem. If this bending would have been less, then it is able to bend it. So what do we do as correction of hypermetropia? It is a nearby object. It was going to make them here. Now what do? We put a convex lens here. Convex lens bends them a little. So there is help to this lens, the combination of this lens. Now this is a convex lens, this is another convex lens, their power is combined. If their power is combined, this bends a little, it bends it more. And now this bending makes it meet here. And here the image is now sharp. So this is the correction. So what is the correction? To put a convex lens before the eyes in case of hypermetropia. So that was myopia, this is hypermetropia. These are two defects in the eyes which can be corrected by these two, and now we'll make some numericals on this. These are the parts which are mostly asked. This part, the numerical part of it. So you must be very clear about it. Okay, now we go for numerical for hypermetropia correction and myopia correction. In myopia correction, our formula is 1 upon B minus 1 upon U is equal to 1 upon F. Now in this, the person is not able to see faraway things. He is able to see at a distance of 6 meters. At a distance of 4 meters, like that, but not beyond that. That means, where is the change? The answer is, the change is at his far point. Let the far point be P. P meter. A person is able to see up to 3 meters very clearly. Beyond that he cannot see. Then what does it mean? His far point is 3 meters. Okay, so his far point is P meter. That means if there is an object at 10 meters distance, he will not be able to see it. But if we have a device which will bring that object at 10 meter, make its image at 3 meter. Object is at 10 meter, where the image is formed at 3 meter, then his eyes are good enough to see at 3 meter, and he will be able to see it clearly. What does that mean? It means that our U is U, of course. This is what? Object far off. So far off object is, how much far off it can be? It can be at infinity. So an object at a far away distance we can take as U is equal to infinity, and where we want the image to be made. The image of this object, don't get confused by image inside the eye. No, we are not talking about this. We are talking about this. That here is a defective eye. This defective eye is good enough to see this object. Not beyond this. This is 3 meter or this is P meter and it makes it clear. Okay. Now we have put an object here. This object, now it goes like this. Now we have to diverge it a bit more. Now this here it is clear, but the object is here. So we put the object here. So this distance will be known as u. Here where he can see it clearly, what we call it, far point. Far point. This will become v. That means this object has to be brought here by this lens. So we are not talking about this lens. We are talking about this lens. The lens of our spectacles. चश्मे का कांच ये है. चश्मे के कांच का काम क्या है? जो चीज इंफिनिटी पर है, जो चीज इंफिनिटी पर है, उसकी इमेज यहाँ P पर लेके आना. ये P क्या है? फार पॉइंट. क्यों यहाँ लेके आना? क्योंकि यहाँ पर हमारी आंख को क्लियर दिखता है, इसलिए उसको यहाँ पर लेके आना है. So what is this distance known as? V. What is this distance known as? U. U कितना दूर हो सकता है? तो U इंफिनिटी तक हो सकता है. और V हमको कहाँ लाना पड़ेगा? P पे लाना पड़ेगा. यहाँ हमको V लाना पड़ेगा और यहाँ पर हमारी आंख क्लियर देख सकती है. तो फोकस कितना होगा? F. Now we make this relation as 1 upon V minus 1 upon U is equal to 1 upon F. 1 upon V. V is how much? P on which side? On this side of the lens, and this side is negative. Minus P. Minus 1 upon infinity is equal to 1 upon F. So this becomes 0. So what do we get here? F is equal to minus P. It has become a very simple relation. This minus shows that the lens to be used is a concave lens. And P is what? P is our far point. So that is our focal length. Now this makes it a very simple thing. If a person is able to see only up to 80 centimeters and beyond that things are not clear, he can see only up to 80 centimeter. Then what should be the focal length of the lens he should use? The answer. Number 1, he has the defect of myopia. Defect. Number 2, he must use a concave lens. Number 3, the focal length of the concave lens should be 80 centimeter. Why? Because we have already proved that F is equal to P by this. So you should be able to derive this. The object is at infinity, the V is at far point, therefore 1 upon F is equal to this, so F is equal to far point. Again, a person can say a person can see up to 3 meters. So what should be the focal length of concave lens he should use? Answer, 3 meter. Okay. So if F is this, then how much is the power? Power, you know, it is 1 upon F in diopters. So you can very well convert it to diopter. Now let's make a small numerical. A person cannot see clearly beyond 2 meters. A person cannot see clearly beyond 2 meters, then what he should do? So far, what is the defect are in the eyes and what he should do? We know he cannot see far away. So what is the defect? We will write myopia. What he should do? He should use a concave lens. Okay. What should be the power of the concave lens? So we know that f is equal to far point. And far point, I have told you, 2 meter. We cannot see beyond 2 meter. So f is equal to 2 meter. So power is equal to 1 upon f is equal to minus 1 upon 2. This is equal to minus 0.5 diopter. This is power we will use. Okay. Now if I cannot see clearly beyond 1 meter, then what is the focal length I should use? 1 meter. What is the power? 1 diopter. So this is how the numbers are formed. This is how the power is calculated. So you must practice on this. This is the part which is mostly asked from this topic. That what should be the number of classes, what does it mean, and how it is related to far point. So remember again, the far point gives this is the far point, this gives the focal length, and 1 upon f in meter, this gives you power. So this is correction for myopia. Now correction for hypermetropia. If we are not able to read the books, what do? We cannot see nearby things. We are bringing a book, making it close to us at 25 centimeter, and now we want to read it. We are not able to read it. Why we are not able to read it? Because there is a defect in the eyeball and the image is formed far away. But if the object is at a distance of 2 meter, we are able to see that clearly. We are able to see the blackboard clearly, but not the book. Then we have to put a lens before the eyes to help. We have to find characteristic of this lens. How to find the characteristics of this lens? So we have to find its focal length. What do we know? We know that we are able to see at 2 meter. What is that point known as? The answer is that point is known as near point. So our question says near point of a person is 2 meter. What does that mean? He cannot see earlier than 2 meter. Things are not clear to him. When the things become clear, when it is at least at a distance of 2 meter. That means if I put a book here, then image of this book should be formed at 2 meter, because he is able to see the things at 2 meter very clear. Now try to relate it with u and v. What is this? This is u. Where is the v? V is there at 2 meter. So what is v? V is the near point. And what is u? Where he has put the book. Where do we put the book? Normally we put the book at 25 centimeter, and that is D, or 25 centimeter. So this is our object distance, because we are putting our newspaper here. But the image should be formed at 2 meter, because we are able to see clearly at 2 meter. The V should be near point, 2 meter. Okay. Near point, let it be N. Then how do we set it? We set it again, 1 upon V minus 1 upon U is equal to 1 upon F. Now here 1 upon U will be D. Okay, here we have to form here we have put the object. Object is here, our book is here. And this is near point, near point. Here we must form the image. So this distance will be V, and this distance will be U, and U is equal to D. Okay. So with the sign convention it is minus D, and 1 upon V. 1 upon V is the near point N. So this is equal to 1 upon f. 1 upon f is power itself. So this is 1 upon n plus 1 upon d. This is our formula. Okay, let's put it with the values. If we have put the book at 25 centimeter, that is 0.25 meter. So this will be 0.25. The nearest point where a person can see is 2 meter, not below this. So this we will put as 1 upon 2 meter. This is the power. This is equal to 1 upon f. This is power. So this will be 1. Okay, we will make it 2, and this is 1, and this is 2. So this will become 9 by 2. 9 by 2 is 4.5. So this will be power of the person required to read the book. So here you will see the sign coming is plus. Plus sign, what does it mean? It means the lens should be convex. Automatically your answer will be positive. And 4.5 is what? Power. Power is equal to 1 upon f. And now if they ask what should be focal length, so no problem. Focal length is equal to 1 upon p. So this is 1 upon 4.5 meter. This will be focal length. But normally what is asked is power. So power of the lens will be plus 4.5. Again see it. The formula is 1 upon b minus 1 upon u is equal to 1 upon f. 1 upon f we put as power. Where is the object always kept? Object is always kept at 25 centimeter, that is 0.25 meter, and negative on this side of the lens. Okay, this minus here. 1 upon v. V is what? Where we want to form the image. Where do we want to form the image? Whatever is the near point. If a person can see clearly at 3 meter, then we will write it 3 meter. If a person is able to see at 1 meter, we will write it 1 meter. So, if a person is able to see at 1 meter, we will mark it as 1 meter. And again solve it. This will become minus minus plus. Again we will solve it. It will come 2. Here 1, and this is 1 plus 4. This is 5. So we will need a lens of 5 diopters. So this is how we will make it. So remember this method for hypermetropia and that method for myopia. These are the two things you must practice more, because this is the things which is asked mostly. The description of eye is not, I don't think it is a very important thing for point of examination, because there are many other things in the array of things which are to be asked. So description of eyes is mostly not asked. But what is asked? Remember, what is accommodation? Number 1. What is far point? What is near point? These two things. Then in numerical, having far point and near point. So these are the things which are asked mostly. So be prepared on these numericals, on those definitions of accommodation, etc. So it is all about the eyes, what we are supposed to study. Another thing, when the eyes are relaxed, we have done it. When the eyes are relaxed, when the rays are coming parallel. When the rays are coming parallel, then our lens is set to make the image on the retina without help of any muscle. There is no stress on the muscle. That is natural focal length of our lens. But when the things are coming closer, then we have to increase power of our lens and the muscle have to press it. So, but there is a benefit that when it comes closer, we see it more clearly. But we have to pay a cost. What is that cost? The cost is that our muscle have to keep pressing them. So they will always be under stress. So if you are seeing a computer monitor continuously, like now you are doing, that means your muscles are pressing the lens because you have to accommodate a very nearby object to see it clearly. But the moment you see a far off object, the lens are released. So these are two features, remember. Whenever you want to see a thing very clearly, it must be brought to the distance of distinct vision D, but you have to pay a price. The eyes will be under stress. So if you want to keep the eyes relaxed, then let the rays should come parallel, the object should be at far away. So these 2 points we will note and we will use them in the next topic, that is magnification. Thank you.